Pardon my brother.
Right, yeah. Okay, everybody back, all ready to rock and roll again? See where we are. Right. Okay. All right, we'll progress on. Quite appropriate for the weather conditions up in Scotland. Engine ice protection. And I'm sure if you've been going up Everest, you might need this a bit as well. Okay, so we'll look at types of ice protection that engines use, a few different systems, and when we're going to use it, and other bits and bobs that go with it as well. Okay. Right. So we're going to look at two main types of engine ice protection. There's going to be the hot air version, and there's going to be the electrical version as well. And the two methods of both of those is anti-icing and de-icing. Now, the hot air, we actually take a tapping from the engine, and we use some of the air from the bypass, or certainly from back of the compressor, somewhere about there. We can put back into the front of the engine, and that helps protect from the blades from icing up as well. Again, positives and negatives on that one. Electrical one, we can actually just tap in. We've got electrical power supply on the aircraft, so we can use that as well by various types of methods. Now, the two main methods are called anti-icing and de-icing. Can anybody tell me what the difference is between anti and de-icing is before we look into it?
Anti-icing means it prevents to form ice.
Yeah.
De-icing means it allow to form ice. After that, it will break that ice.
Yeah, that's right. So the two methods we can use, the anti-icing tends to be the hot air type. The de-icing tends to be, especially in turboprop aircraft with propellers and that sort of thing, electrical. There is another method we can use on the aircraft. We can use pneumatic systems that blow bellows up and that, and the wingtips. But again, excuse me, we're just looking at the engine side of things. Okay, and just curiosity, just to go back a bit, I was mentioning about the intakes for some engines. If you look at this intake here for the engine on the photograph, that's like a scoop type intake. I mentioned that on like an F-16. That's also in a propeller aircraft. But yeah, you can see an intake there. These type of aircraft, or the turboprops, will tend to use an electrical system, although they can use both if required, depending on the type of aircraft. But that's the main types, is hot air electrical and anti-icing and de-icing. We'll look at these a bit more in depth now. So turboprops mentioned there. Again, turboprops tend to use electrical power, but can be a combination of both, but they tend to be just electrical power from the engines. The turbojets, generally using hot air, as I said already, take a tapping of, let's come in. You take a tapping from somewhere about the HP compressor area, okay, delivery air, nice hot air, so that's definitely going to prevent the icing from forming on the front of the intakes and that sort of thing, and we blow it back into the various connections on the intake of the engine. Now, that's all very well. Hot air prevents the ice, but if we put hot air back into cool air on an intake, what sort of problems might we have with the engine? What potential problems could be ingested in the engine? So we're putting hot air back into the engine. Prevents ice, that's great, but what could potentially happen?
It will decrease the performance of the engine.
Yeah, it's going to.
If we bleed out the air from the engine core.
Yeah, we're taking a bleed, so we're taking some extra air off. Now, the engine's designed to bleed, that's okay. It's more the putting hot air back into the engine. You're quite right, it's going to take a bit of power off it. We are tapping a little bit, but it's more the fact that you're putting hot air. Now, we're sort of making an analogy of that is if you're going for a run. Now, if you're going for a run on a nice, cool, dry day, you feel quite energetic. You get nice, fresh, crisp air into your lungs, you can go for a run. If you go for a run in the same sort of time, but in a hot climate or a hot day, you start breathing heavier, don't you? Because the hot day, there's less oxygen because the molecules have expanded. So you're having to breathe in harder to get more oxygen in. Where on a nice cool day, the molecules are small, lots of oxygen is compacted, so you feel a bit, a bit better. Same for cars. On cars, motorbikes on a cold day, they will run a bit better because, especially on a dry day, a nice cool dry day. On a hot day, they just feel a bit tired and that sort of thing. Pretty much the same as us if we go for a run on a hot day. Well, the same goes for engines, turbojet engines. If you put hot air back into the compressor, it's rebreathing its air. It's less oxygen in there, so it's going to have to go faster to get more power. So some of the older engines, they would lose about maybe 2% thrust. And part of the checks you have to do is you do a full performance run where you'd start the engine up, put it to full power, check the figures, bring it back down, then switch your anti-icing on, take the power back up to maximum, and then check your figures again. And then it should be no more about 2% thrust. Nowadays, though, most of the new type engines, they're what we call as over-designed. You can put whatever you want on and they will cope with it. But certainly on the older jets, you would suspect, or you definitely expect to see a slight decrease in thrust, purely because the engine's trying to breathe hot air. Okay, so again, it does the job. It prevents the icing, but you have to be aware that it potentially can lose a bit of thrust on the engine. Okay. Nice, dead and simple. There's a little rubber tip on the actual cone on the front there. Okay, all it is, a little rubber tip that is slightly off center. So as it's going around, it's just vibrating a little bit. And that just stops ice from forming. Dead simple, no heating, no electrical, no air required. Just the fact it's a rubber tip, it vibrates a little bit, it prevents the ice from forming up. Nice and easy, dead simple. Oh, sorry, go back a bit. Mentioned on the intake, the air that gets tapped, it can go to the front of the spinner, or the nose cone. It can also go to the very front of the intake, with these little tiny holes that allows the air to go back into the intake as well. Okay. As well as that, you'll also have, I forgot to mention, my fault, you'll have a regulating valve. We can't just take air straight from the back of the compressor. We need to regulate the pressure as well. And on these type of systems that are meant to get photographed, there's two valves. Now, the two valves will have both open. It's a backup redundancy plan. If one valve fails, at least you got another one. You know, it can open up just in case one fails. So better to have two than one, just in case you do go through that scenario. Again, rubber nose one, dead simple, rubber cap, nice and straightforward. A basic sort of generic layout of the anti-icing. You'll have a control panel to obviously for the valves, be maybe two valves, first valve and the second valve. You have a valve that bleeds air back into the duct, and you have a modulating shut-off valve. And now I've got their fifth and ninth stage, that's where you could be taking a tap, and this is a generic one. Your anti-icing valve, which allow the hot air to go to the front of the engine, and some sort of regulator to regulate how much air that goes in. Don't want too much, we need some obviously. Okay, that's just a typical example of one. Now, high power thrust settings, as I say, can cause icing section to occur at fairly high local temperatures. What I mean by local temperatures, the temperature today out in Nepal compared to the temperature today in Scotland, slightly different. Now we've got probably about, I think it's about 8 degrees maximum today, maybe not even that, probably about 5 degrees. And there's a bit of moisture in there. So very cold, bit of moisture, there's a good chance that it's going to freeze if we're doing high performance runs. Now temperatures as high as 26 degrees. I mean, how hot? I've been out in Nepal a couple of times thankfully, and it does get quite warm. It's a hot day, it's quite hot, isn't it? What's the sort of temperatures out there again in a hot day? Out in Nepal. Yeah, so you're not far off what we're saying there. And you're thinking, oh, that's Sanjeev. I'll get back in a minute. Yeah, so you imagine that temperature out there, you think, well, that's too hot for ice. But if you've got a lot of moisture in there, now out in Nepal it's quite dry, so it's not too bad, but certainly some climates can be quite humid. Now, if you've got high temperature, say 23, 26 degrees, and it's a very humid day as well, okay, by the fact you've got fast moving air, pressure's going to be less, temperature's going to be a lot less, you can actually have ice forming up on the ground when you're doing high performance runs. So when you put your aircraft intakes or protection guards on your engines, when you're doing performance run, watch it doesn't go very white very quickly. And it does. I've seen it on jets I've worked on where we know it's sort of borderline for being icing conditions. So we've had a safety person outside, and as we go up to full throttle, we keep an eye on the intakes, and it literally goes very white very quickly within seconds. And obviously, if you block your intake off, there's a chance you could surge your engine. So be aware on even a warm day, 26 degrees, with high moisture present, that on a high performance run, you could potentially have ice formation on your engine guards. Otherwise though, normally a figure of 8 degrees to 10 degrees, pretty much was here in Scotland at the moment, would be visible moisture present. Okay, good figures to write down or make a note of. I know you've got your old books at the moment, but in the books I think it's the same in the old books if I remember right. Okay, but if not, just make a note on the book somewhere so you can write it down later on. That's good questions to remember, shall we say. Okay. Electrical system. If you bear with me, I'll just check Sanjeev's. I'll be back in 2 seconds, okay?
लामाजी सुत्या
सुत्नलाई अब निन्द्रा लागिरहेछ आज लास्ट थाक्यो नि
लामा सर
काम थियो
लामा सर
हजुर भन्नुहोस्
फर्स्ट बेला चाहिँ निदाइन्थ्यो यार होइन अहिले त के हो खाटमा भन्छ न मस्ती हुन्छ नि
त्यही भने आज फेरि अलिक थाकियो पनि के यस्तो निन्द्रा लागिरहेछ हिजोको एक त्यस्तै छ
ओ बारसाई
ल गुड नाइट है केटा
ल गुड नाइट दाइ
राइट निन्द्रा त मलाई नि लागेको जस्तो भइरहेछ
2020 को किताब दिन्छ र
अब दिन त दिनै पर्यो
दिनै पर्यो नि
के दिनु पर्यो रे
किताब दिनै पर्यो भने नि किताब दिन्छ र भन्नु सक्दैन
किताब त लिनै पर्यो नि कहाँ छोड्नु हुन्छ त भोलि गएर मागिहाल्यो
हाम्रो गल्ती भयो फोन गरेर नि प्रिन्ट गरेर राख्नु भनेर भन्यो
अनि फिर्ता गर्न मिल्दैन त कोरिसक्यो त एउटा किताब त
फिर्ता गरेर के काम हो उनीहरू के काम गर्यो
गर्नुपर्ने किताब त्यही भने अघि कहाँ पुगे यस्तो भएको भने एकछिन त भने म त अगाडिको इन्टेक छैन इन्टेक भन्ने छ नि त्यहाँ हेरेर बसिरहेको कहाँ चाहिँ के पढायो भनेर हाइलाइटै गराएन त लाज किन
17 पनि यसले क्लास लिएको
लाइन टु लाइन गराएकै छैन है यसले सत्रको त लाइन टु लाइन पढ्यो नि त
Right, back on. Sorry, guys. I was just checking Sanjeev. He's going to be getting the books printed out as soon as he can, and he'll give you the new copies as soon as he can. So hopefully, I would say by the end of the week at least. It'll take a while to print all the 4 books. So, say the 4 books, it's pretty much the same material, but it's been moved about, some new stuff put in, some more stuff taken out, and we've also got questions in the book for your revision, which makes it good for revision. Okay, so hopefully we'll get that sorted for you soon. All right, moving on, we've got electrical system. And with electrical system, we are just taking electrical power from the engine, and we're going to have certain parts of intake, and this is a little simplified diagram. You might have continuously heated parts, intermittently heated, and the blue parts being electrical elements themselves. Now, what it is, we don't always put it on all the time because that will drain a lot of electrical power from the engine. But we will look at cycles of how it's operated and the types of where you actually find these sort of elements. Usually, especially on propeller blades and that as well, you have a sort of layer or laminate that's been glued on, and you can see sort of blue wiggly lines. That's electrical heating elements that will also heat up in the correct order and sequence. So a typical protection cycle sequence. The first one we're looking at is a fast cycling speed. Now, this is going to activate when there's high temperature with high chance of moisture available as well, so high moisture content. So although it's quite a warmish day, when you're flying high in the sky, also gets a lot cooler. Remember, going back to Module 8, stratosphere is about -56. And there's high moisture available, and there's a good chance there could be some ice. But we don't need it on for long stretches at a time. You can see here, I'll go into the air intake first, then I'll switch off, then I'll go into the propeller and spinner, back to intake, and then have a period where it's not on at all. Okay, we call that a null period. So that, for the fast cycle, is high temperature, high moisture content. Okay, good one to remember there or write down somewhere. We've got the slow cycling speed. Well, that's when it is cold. There's a good chance it's going to build up very quickly. So what we do is we switch it on again, the same air intake, the propeller and spinner, etc. But this time it stays on longer. Okay, so fast is high temperature, high moisture. Slow is, yeah, it's cold. It's definitely going to be ice. Okay, so that's your 2 cycling scenarios there. Let's double check there. Okay. So basically heat on and heat off. In between that, you've got null periods where there's nothing on at all. So again, make a note of these ones, make a note of the 2, because you could be asked a question for a slow cycling period or a fast cycling period. Okay. So fast again, high temperature, high moisture content. Slow, it's cold, it's going to good chance. Irrespective of moisture or not, it's cold, it's going to happen. So it goes back to the previous page where plus 26 degrees, high temperature with high moisture. And down to about 8 degrees, 10 degrees or below, there's definitely going to be some sort of ice. Okay, any questions on that one? That was just the basic heating on that one. Just double check. Covered up. Okay, that's the 2 main ones there. Remember the types, hot air and electrical, and the methods of anti-icing and de-icing. Okay. Which was sort of covered in Module 17. Remember the boots on your propellers. So we're sort of going back away. So we did touch on this now in Module 15, and then as you saw in Module 17, we covered a bit more in depth on Module 17. So the same sort of pictures we had last week. Okay. Any questions there? All happy? Although it's Monday. Okay. No questions. So, oh, sorry, I had you on mute there, guys. Any questions? All good? Oh, sorry, I forgot I had you on mute there. And so everybody's quiet. Right, next period is compressors and fan blades. Okay, we're going to look at the types of compressors, the blades themselves, and a bit more component build-up of it. So the one we're looking at there, we've got a compressor at the front. Okay, then we've got the one in red, which would be your HP compressor, and obviously attached to your HP turbine, and then the LP compressor attached to the LP turbine. So you can see the yellow shaft there for the LP and the one in red for your HP. And remember, it's the HP one that turns first. So there'll be a gearbox underneath here, and there'll be a drive shaft that touches the HP shaft, which will spin first to turn the engine, and then that'll start the engine, and then the LP one will eventually turn as well. So, looking at that one, I can just see there, you've got the big fan, okay, attached to the LP compressor. Now, we'll come on to it already. I think I mentioned module 17 as well. But remember, we call that a booster. A big fan blade attached to the compressor, we call that whole assembly a booster. Americans call it a booster. So, two types of compressor we're going to look at. First one is centrifugal. And the next one is what's called an axial flow. That's the two main types of compressor we're going to speak about. So remember those names. Centrifugal, okay. Now, the centrifugal one is the air comes into the compressor, as we saw before. But this time, as the centrifugal compressor spins, it throws the air not back the way, but out the way radially through centrifugal force. Right? So quite a compact, quite a large compressor, quite a heavy compressor as well. Very robust, very strong, very basic, and not quite as efficient as an axial flow one. Axial flow one, as it sounds, it's on an axis, so axial. So the air comes in, and the air goes back the way. All right, hence the name axial flow. Centrifugal flow, centrifugal process. Okay. And in centrifugal type, you have the impeller. So this is the front of the compressor. Air's coming in here. It hits the vanes. As it spins round, the air gets thrown out radially, and then we'll hit what's called a diffuser. Now, diffuser is also shaped divergent shape. So the vanes in the centrifugal compressor are divergent, so like a V shape like that. So as air hits it, it throws it out, it increases the pressure, obviously temperature as well. It'll then get thrown out to the stationary diffuser, so it goes up here, and then eventually that will go out. There's a diffuser there, and then as it escapes through there, it will go to the combustion chamber. So there's your impeller rotating round clockwise in this case. You can see here there's the vanes of the impellers, divergent shape, so as they're spinning out, they're increasing pressure and temperature, and as the air spins out and gets collected by the stationary diffuser vanes, they are also divergent in shape. So it's a pressure rise, temperature rise, pressure rise, temperature rise again before it hits the combustion chamber. Now, the impeller tips reach speeds of about 1600 feet a second, so quite fast. And it limits the pressure ratio. You get a pressure ratio rise of about 4.5 to 1. So you need to know the pressure rises for a centrifugal compressor and an axial flow compressor. So centrifugal is 4.5 pressure rise increase. Okay, so quite a substantial amount. So it's a high pressure. Imagine the temperatures. The temperature's going to be quite high as well. Unfortunately, you don't need to remember those ones, but please remember the 4.5 to 1 for a centrifugal compressor. And then there's the breakdown again. You can see the compressor, there's the diffuser, and then eventually these will go into the ducts for the elbows we call them before it goes in the combustion chamber. Okay. Now there's various types. You can have single, double acting, twin, and that sort of thing. But again, we have some sort of casing from here. So intake, there's your impeller. In this case, not the best diagram, to apologise. You have some sort of swirl vanes to control the air, and as it comes in, again, there's diffuser. Intake chutes which direct the air into the elbows, and then these elbows here and all the way around, these will be connected to your combustion chambers. There's a shaft, okay, which will be connected to your turbine. It'll be back here somewhere, which is obviously connected to the compressor. So as the turbine starts to spin faster, it will spin compressor draw more air in, and so on. Okay. Advantages though. Now a good picture as well. Here's a single impeller, and here's a double impeller, basically one back to back. You can have two of these, maybe in tandem, or back to back as well. Again, the size and weight of these, they are robust, but again, the weight is a massive disadvantage. So advantages are, they're simple, easily made, quite cheap to manufacture, and very robust in construction. In other words, they will take a lot of damage. If it sucks something that shouldn't be in there, a little stone, it'll take it, but it won't do a lot of damage. Okay, it'll spin it back out. So less vulnerable to damage. So quite some good advantages there. But they're heavy, you know. So disadvantages are high speed of rotation required. We've got to spin these really, really fast to make them very efficient. Okay, so that's going to take a lot of power. A large frontal area. Now you might say, well, wait a minute, look at an axial flow compressor got very big blades. Yes, but if you to do the same sort of power for these ones, they are a large frontal area. Limited pressure ratio, 4.5 to 1, that's it, thereabouts. There's not increased pressure rises. But yes, we get high pressure rise, but downside is we also get high temperature rise. Now, high temperature, we'll come and discuss later on. Compressors are described as being efficient by how much heat you lose, okay, or retain. The more heat a compressor can keep within the engine, the more efficient it becomes. The more heat it loses, the less efficient it becomes. Well, these have got high temperature because of high pressure, and unfortunately, they tend to lose a lot of that energy from there. So in other words, a high temperature increase. That's the main disadvantages. So just run back through those again. Well, it's simple, cheap, robust, less frontal damage, good. However, high speed rotation required, large frontal area, limited pressure ratio, and high temperature increase. It's not so good. Okay. So what they're made of? Well, the unit construction is usually forged from an aluminium alloy, main unit. The radial vanes are what you class as an integral part of the impeller, and they're machined out of a forged blank. So it's a nice simple process. Rotating guide vanes, often made out of steel, to resist impact damage, and they're splined onto the actual aluminium impeller itself. Some other impellers, they do have rotating guide vanes, are aluminium, forged at the same time and out of the same block. It makes sense, use the same block as the impeller and disc and radial vanes are. Although the early ones made out of steel, the modern ones now, impellers are made out of titanium, a bit more robust. Again, it makes it a bit lighter, but stronger at the same time. So they do improve a little bit through time. And they're constructed in one piece, again, so the impeller disc, vane, and rotating guide vanes are all integral. So it's one big lump. So if that gets totally damaged, you'd have to change the whole compressor. And as you'll see later on with axial flow compressors, we can change blades. So although this is very robust, it can take a bit of damage. We also use these type of compressors in smaller engines like APUs, auxiliary power units, small starters and that sort of thing, and various other ones as well. So that was a centrifugal type compressor. Okay. So then we're going to look at the axial flow compressor, which is the main one you'll probably work on. Centrifugal compressors, you'll probably come across them on museum aircraft, to be honest. Maybe some small engines, APUs and that. But apart from that, your standard run-of-the-mill will be the axial flow ones. And this one we've got here is just a single spool. So it's just one compressor and obviously be one turbine way at the back here. You have your intake, the front of the engine. And as you can see here, the blue, sort of greyish colour, they're the rotors, they're the ones that actually spin. Then after every rotor, you have a stator, a stationary blade. Okay, so a rotor and a stator makes a stage, as we said before. Now again, these are divergent in shape, so as the air goes back each stage, it compresses, compresses, compresses. But as you can see here, this casing here, the straight part, against the drum, called the drum where the blades connect to, forms a convergent shape. So that maintains the actual velocity of the gas going in. So we don't lose the speed of the air as it gets compressed, 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 but it would do normally. Because if that drum was straight, then the airflow would just get really slow. And by the time we go back here, it'd be hardly moving. Yes, the pressure would be increased, but it would be hardly moving. So we have large blades at the front. The drum gets wider towards the rear, which means we have smaller blades, and that maintains the actual flow velocity. Okay. And this is what I mean by what's going on. So there's your rotor, the blue and the stator. So non-moving part, non-moving part, etc., etc. So the air comes in. You can see the pressure rise going up here, and between each stage, we see the speed goes up initially, and then as it gets compressed, it goes down, then goes up, goes down, goes up, goes down. And because of the shape of the compressor, the speed, if you were to average that line out, the speed pretty much stays constant. Okay. Now, centrifugal compressor was 4.5 to 1. The pressure rise per stage, that's every rotor and stator, is 1.1 to 1.2 to 1. So a smaller pressure rise, but you tend to find in axial flow compressors, we have more stages, whereas centrifugal was just one big stage, and that was it. You could have maybe a twin centrifugal compressor. We've got an old engine in the hangar called a Dart engine. It's got a centrifugal compressor and a slightly smaller centrifugal compressor behind it. So you do have a twin stage one. But axial flows have at least 4, maybe 8 stages. So for every stage, every time that pressure builds up there, it goes up roughly 1.1 to 1.2 to 1 pressure rise. So nice, smooth, incremental pressure rise. Now, also with that, as I said before, when you increase pressure, you also increase temperature. So temperature rise, as well as being 1.1 to 1.2 pressure rise, we also get an increase of temperature of 25 degrees C per stage. So by the time it gets to the back here, it might have gone up by 10 stages. Well, there's 250 degrees by the time it gets to the back of the compressor. Okay, thereabouts. Depends how many stages, obviously, in the compressor there are. So good numbers to remember. Make sure you write these down or highlight them. Pressure rise 1.1 to 1.2 to 1 and 25 degrees C. Okay. And just like the centrifugal compressor, before we get to the combustion stage, so the compressor's done its job here, it's compressed the air. We then also have a diffuser. And just like the diffuser in the centrifugal compressor, it is also divergent. So just like diffuser, divergent. Yeah. So you see there, so small area here, as it comes towards the combustion chamber, it diverges out, so it slows down, and it's the last chance pressure rise before it goes into the hot part of the combustion chamber. Okay, so it just helps slow it down, stabilize it, last chance of pressure, and then it'll be suitable speed and pressure for the combustion chamber. And so diffuser on both engines, just slightly different ways of doing it. Where the centrifugal one spun the air out and the diffuser caught it and then spun it out again, the air this time is going actually from front to back all the way through. Yeah. So types of axial flow compressor, which just relates back to the types of spool. So you've got single spool, twin spool, etc. Yeah, same sort of thing. And then triple spool as well. All depends on the type of engine. Single and twin spools tend to be military aircraft, and some larger twin spools were American sort of commercial aircraft back in the day. High and low bypass, mentioned already. Bypass ratios can be as high as 5 to 1. That's way above that now. Some of the new engines, Trent engines, I think it's a Trent one, again, they can be about 10 to 1. So massive amount of bypass. All right. This one I showed you earlier, a low bypass, twin spool. There's your LP compressor, LP turbine, and HP compressor and HP turbine. So relatively low bypass, maybe 1 to 1 or 2 to 1 bypass ratio there. It's certainly a lot higher nowadays. So again, the twin spool there, just showing you all what's going on with each part. Okay. As I said before, most of your power on a high bypass engine is transmitted out through the cold stream, and the air it's getting bypassed we call the cold stream. The air it's going through the core engine we call the hot stream, strangely enough. So in a high bypass engine, we're getting the thrust pretty much from the fan blade attached to your compressor. Now, I said before, a fan may be fitted to the front of a single or twin spool compressor, and indeed a triple spool. And that fan, as I said, attached to the compressor, we call a booster. Okay, a booster. So that whole compressor assembly is called a booster by attaching this large fan blade to the compressor behind it. All right. And you see in this engine, just to be different, we've got a natural flow compressor, and then we've got a centrifugal compressor as well. We're just being greedy. So depending on the type of engine, you can have a mixture of both. And we've got some examples back in the hangar here at Scone where we've got a small starter engine, and it does have an axial flow compressor with a booster radial compressor at the back. Why? Because they can. It's just the way the designers have gone for it. Okay. There you go. Very often the LP compressor fitted with a fan is called a booster rather than an LP compressor. Okay. A rooster booster, as I call it. Triple spool, as we were saying before, you've got a spool within a spool within a spool. Okay, so LP compressor at the front, your IP compressor in the middle, in between, so that's where I got intermediate, and then your HP compressor at the back. So you have a shaft and a shaft. You can see here the HP drive shaft is quite big. Then we've got the IP one in between, and then the smaller shaft, or the thinner shaft, is in between those. Okay. And you can just see, just sort of stepping ahead there, this part, I might actually colour this in next time. This is taken from the gearbox. Here's the gearbox attached to your engine. On the front of the gearbox, sorry? The gearbox will have a starter motor on it to spin the gearbox. The gearbox will spin a shaft, you can see here. And that shaft there, you can just about see it where my laser light is. That's attached to your HP shaft. Okay, so that will turn the HP shaft. That will start the engine. Then the IP shaft will start turning. Then the LP shaft will start turning as well. So it's a small HP shaft that will spin. Okay. Materials, again, casings, good old magnesium or aluminium alloy at the front, and steel at the rear for a bit more strength, and obviously for heat as well. But it also gets hotter as it goes back, so there you can see the airflow going in. All right, rotor blade followed by stator makes your stage. Fastened to the rotor are rows of blades. Again, now the blades are also made of a light alloy. Okay. Or possibly steel towards the back. They tend to be lighter out at the front, bigger blades, and the smaller ones towards the back are steel. This one shows you an LP compressor and an HP compressor behind it. HP compressor being the bigger and the low pressure compressor being in between. On this one, we can count the stages. 1, 2, 3, 4, 5, 6, 7, an 8-stage LP compressor. I can just about make an HP one. 1, 2, 3, 4, 5, 6, 7 stage. Okay, so an 8-stage LP and an 8-stage HP. Now, again, remember your annotations. We practice those. We've got N1 for the LP. It can also be in the cockpit. It can be described as N1. It can also be NL, low pressure. And the same for N2. N2 being your HP can also be NH or N2. Unless it's a triple spool, which should also be N2. But normally, let's speak about twin stage or 2-spool engines. The blades will vary in length. Let's say you also have the bigger blades to the front, and as the drum goes back, you tend to have the smaller blades at the back. Okay, ones at the front say usually a light alloy, and the shortest at the rear usually the steel variety. They can absorb more heat. Various types of fitment for the blades. Some just slot in position with certain tab locking in them. Some can be secured with various fitments. It all depends on the type of engine you're working on. Okay. Should be looking at this diagram. Right. So let's sync there. Now, going back to your Module 8 aerodynamic days, do you remember what the twist of a wing was called from the root to the tip? Remember what that was called? Module 8.
Washout.
Washout, good, yay! That seemed like months and months ago, I'm sure. Years ago. Yeah, well, in a blade for the compressors and even the turbine blades, we call it stagger angle. It's pretty much the same thing. If you look at the twisting of the blade here, pretend this part here was a fuselage of an aircraft. So we're looking into the blade tip. Yeah, so it varies along the length of the root to the tip. Yeah, and again, The bending down point is like the wingtip, goes into the airflow, just like we saw on a wing. And again, it does the same job as a wing. It's maintaining that the airflow velocity over the wing constantly. We don't just have one part of that blade making most use of the airflow. We have the whole blade working as a wing. That's pretty much what a rotor blade or a turbine blade is. It's a wing, but it's just spinning around. That's all it's doing. Same for propeller blades. Okay, so we call that twisting of the angle, we call it stagger angle on a blade. It is the same idea as washout, though. It's the same job. Okay, so nothing too hard there, hopefully. Again, fitting of these ones, you can fit them in individual vanes or segments of vanes. Some slide in. Now, the ones that slide in, again, we used to be able to do this in the hand. We can't do it anymore, unfortunately. But we could take these segments out, and then to stop these shrouded vanes sliding all the way around, there'd be maybe about halfway around the casing, there'd be a plate, which once you put the bottom ones in, you put the top ones in, that plate goes in between, and that stops them because potentially these could slide all the way around, just be purely because of the aerodynamic forces. So these sort of keeper plates we'd have halfway around would stop them from sliding. Otherwise, you might have a simple retaining screw. So the stator ring's in a ring, and some sort of retaining screw also stops them moving. Again, it all depends on the type of engine. Fan blades, high blast ratio fan blades will produce about 75% of the thrust for that engine. In other words, that cold steam air is about 75% engine thrust, only about 25% come to the core engine. All right, so the blades themselves, a containment ring is necessary around the fan, and the heavier the blade, the heavier and stronger ring. Now you can imagine there's an engine in a test bay. These blades here, you see the size of the guy here, look at the size of the blade, it's almost the same size as him. These are turning at quite a fast rate, so the force exerting these can be quite a lot. Now, what would happen if one of those snapped? We don't want to go down the core engine. Hopefully, we want to go out the bypass, just outside the air. So you need a containment ring. The containment ring makes it so that if the blades do snap, it should flip and hopefully go down the bypass, and hopefully land somewhere safely, not hit anybody. So, as it says there, containment ring is shaped to flip the blade with a bit of luck. Typical fan blades, you'll have two main types I'm going to speak about. This one here, that's called a narrow chord blade. Okay, long and thin, called a narrow chord blade. Strange enough, the one beside it, it's called a wide chord blade. Nice and easy. Okay. Now the main difference between a narrow chord and a wide chord is this part here. It looks like a fin, all right, that's been stuck on the side. Now, because this blade's quite long and narrow, it needs a strengthening point. So this looks like a shark's fin on there. And we call it a mid-span shroud, also known as a clapper, also known as a snubber. Okay, so three names for the same thing. Mid-span shroud, a snubber, or a clapper. And the reason it's called a clapper is, if you ever listen to an engine slowing down, you hear this ting, 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 as it goes round, yeah? Sometimes it's these just touching each other, or it could be the blades. Positive thing on this is it strengthens the blade, but it also causes a bit of drag. Again, some of these narrow chord blades aren't actually that narrow, they're almost the same size as these. But the purpose of the wide chord blades, you can see here it's a little wider, about halfway down. It doesn't need the strengthening point. It's quite solid as it is. Okay. So this little fin here, snubber, mid-span shroud, or clapper, three names for the same thing. So advantages of blades are that are lighter for wide chord fan blades, shorter, so less load on the root of given RPM. You had all that strain at the root, and they move more air for a given RPM as well. Because they're wider, they will move more air. They're able to centrifuge FOD, foreign object damage. In other words, anything that goes down there, it shouldn't be going down there. Birds, etc., tools, anything else, it shouldn't be in there. And thus protecting the core engine. More rigid, do not require the mid-span shrouds that we saw before. And allows a cleaner airflow to the fan duct and less drag. As a result, less energy losses. Okay. So you get, plus, let's just show a comparison between the narrow chord and the white cord. You can see the ring there. So there's your snubbers going all the way around. Okay, and then there's a comparison to the white cord one. Far more efficient. Okay. Again, fitting the fan blades in, various types of methods. Some have spacers in between each blade, some sort of spacer, and it might be just a bolt that goes through the end of the spacer, and there's not much that actually holds these in. It's quite, when you take one out, there's not much to it. Has anybody had a shot of taking blades out of an engine at all? Anybody actually taking blades out of any engine?
Not yet.
Not yet. It's good fun. It's good fun. We do it as a practical assessment here. So the guys, we've got an old CF6 engine, quite a big engine, and we get to take. It actually looks like this. That's the sort of blades that come out. It's like a dovetail shape. There'll be a spacer that takes up the space of the blade, and yeah, it's just one little bolt that goes through. It holds everything from coming back out. Not much to it, to be honest. Not much to it. And we get them to take it out, inspect them, and make sure look for damage. Now, fan balancing. So we looked at that. Just going to check there. Yeah, we're okay with that one. I don't want too far ahead before break. Just checking that. Yeah, that should be okay. One thing I said on the previous page is when you're fitting fan blades back in, it will tell you in the maintenance manual which type of lubricant. Usually it's just engine oil, but there might be specific grease or lubricant to put into these slots. Again, only put minimal amount on. Don't put loads and loads on, because what will happen is that grease or lubricant will come out, spray and go over the blades, make it all dirty, and it won't be very good for won't look very good for a start, but will attract dirt and debris, so it's not good. So only put amount and specific requirement. However, we've got all these blades attached to the disc. The disc holds all the blades in. Now, just like a wheel on a car, it needs balanced. Every blade will be, although identical, or should be identical, will marginally weigh slightly different. Okay, because you might replace blades for damage. So again, we need to balance this up. So when are you going to carry this out? So conditioning fan blades will normally be checked visually. You have a visual check first. And if you've got a big engine, look at the front, get a torch, look at the side, and slowly rotate the fan. And the best thing to do is look at the bottom, especially in the big engines. Now, be very careful, because there's a lot of momentum in these engines. If you put your fingers in too far, guess which one's going to win? Okay, your fingers won't win. We've got a good friend of mine, he's one of my juniors. His nickname is Fingers, because he put his fingers in too far to the blade. The blade kept going, his fingers didn't. So he's now got a little bit less of a finger, and his nickname Fingers. So be very careful when you just rotate them slowly. You don't want to spin them very fast, because they will chop bits off. Now, a fan blade with snubbers, which is your narrow chord blade, might develop a problem what's known as shingling. Shingling is taken from the mechanism of the roof tiles on a roof. They call it shingles. Instead of a tile, they call them shingles. Now, shingle, like roof tiles, they overlap each other. So if perchance maybe the engine's had a surge or whatever, and one blade has come over and lapped another blade, we call it shingling. Now, you are allowed to remove the blade, put it back in position, but only for short periods, because as you can imagine, if that blade's come all the way out and gone all the way back, that's put a lot of stress on the root of the blade. So you're allowed to unshingle it, but for only short periods, usually about 20 hours or thereabouts, but probably enough to maybe fly the jet back to its original destination and then replace it, providing there's no other damage. If you find damage, then you have to sort something out. But you can unshingle a blade. Okay. So it says here, blades may be unshingled, well, it contains service for a specific, usually short time, normally about 20 hours thereabouts, providing they can be shingled without causing any further damage. So it's shingling. Only for narrow chord blades, because the wide chord blades don't have snubbers. The task of checking the fan for balance is normally known as a trim balance procedure. When you carry it out, this is going to be carried out when the maintenance calls for it. So even if everything's fine, it might say every so many hours we go and balance the blades. There might have been a report of excessive vibration suspected to originate with the fan. There could be a front vibration capture in the cockpit. Pilot has reported feeling vibration. So again, that may be investigated. So you'll be checking your readings. you might have to put a test kit on there and check the vibrations coming from. Now, when doing vibration, the test kit, again, you'll do specified training. Any course you can go and do, like vibration, non-destructive testing, soap sampling, anything specific, a very skilled extra onto the job you do, you become more valuable as an engineer and more specified. No, you can charge more money, get more money, okay? Get a bigger motorbike. Replacement of a fan blade or blades, including a full set. Yeah, you have to balance it. You put a new tyre on a wheel in a car, you go and balance the wheel. Yeah, same idea for the fan blades. And refitting of a fan blade or blades, including a full set. Okay, which we've done already. Let me take one out. I've got in there again. Following the blending, repair. I'll just make sure I missed that one out. Yeah, replacement. Just double check what I put in there. Replacement, sorry, yeah. It was replacement of the fan blades or refitting, so the same one's going back on. I thought I put the wrong one in there. Irrespective, you have to balance it. Blending repair, so you might have been a bit of damage to the blade, and you are actually allowed to file bits off the blade in accordance with the manual procedures, which is called blade blending. But again, before you do that, if you do find damage on the blades, it's worth checking the turbine, okay? A small bit of damage on the blade might be nothing, that's okay, it's just a little bit. You go and look at the back of the engine, you might find that half your turbine's missing, and we've seen that happen. If you think there's nothing in the turbine, but you suspect something that might have gone down the engine, then it's worth doing what's called a borescope, actually look inside the engine with the special borescope equipment before you go and blend the blade. No point in blending a blade 2-3 hours worth of work, only to find once you've checked inside the engine, it's all damaged, okay? So you think maybe just a little nick, quick blend, make sure you're happy with the rest of the engine first. You might have put a new spinner, the nose cone on front of the disc of the compressor. Maybe it's taken a little bit of damage, maybe a bird's hit it and the blades are okay, they just need cleaned, but the spinner's taken a bit of a bashing, so you've taken it off and put it on. Now, normally spinners will go in a certain position, but you can, and some of them, put multiple positions, and they might have balance weights in there as well. So again, that can affect the balance. You might be able to repair a spinner or a static and balance check on a spinner as well. Again, if it's been removed, refitted, replaced, repaired, it's going to call for balancing. And yeah, you go and do a new untested power plant, you get a new engine, put it in there. Now, that should have been done by manufacturer or the test bed, but again, you might have to go and do a vibration check when you do the power on it, which would be part of your runs anyway. Sometimes, going back to, I'm going to say this one here, if you get a vibration, sometimes just taking the spinner off, rotating it 180 degrees, putting it back on, can sometimes get rid of the vibration as well. Not always, it's a 50-50 hit with that, but again, you'd be following procedure just in case. All right, so there's your spinner, inlet cone, there's the old anti-icing part. Now, you will on your disc have a timing mark. You can mark the blades with a non-permanent marker like a crane. If you're taking a blade off, or a few blades off, or even taking all the blades off, and you're going to put them back on again for whatever reason, you want to put them back in exactly the same place, because if you put them in a different place, that could affect the balance. Although the blades look the same, some will be slightly more worn than others, maybe a bit more damage or being blended or whatever. So make sure if you take a blade off, you put it back on the same position. And same for the cone. Make sure the inner side cone, if it's a twin layer cone, that goes back on the same position. And then the fairing that goes around that, again, make sure that goes on the same position as well. And then finally, the outside cone, that goes on the same position. On the actual compressor disc, there'll be holes for balance weights. These are basically extra bolts with an extra weight on them, and these will be positioned. Now, nowadays, it's done by computer. Sometimes it's still trial and error. But just like a wheel, your wheel gets balanced, a weight gets put on your wheel, and that should take out the heavy spot. Okay, same idea. Okay, any questions on that part? Stop check there. Yeah, if you're doing trim balance, just add on there that's usually done by authorised. So even though you be a qualified engineer, you need to be authorised to be able to do trim balance. It can be a specialist point. The disc itself will be spun up. The blades will be weighed individually in a special environment, and the computer will weigh the blades and then tell you, once it knows the heavy spot of the disc, where to actually fit those blades before it actually gets fitted to the engine. Okay, so make sure you are authorised. Don't just go in with a file and start filing things and weighing things. You must be authorised, and as usual, follow the manual procedure. Okay. All right. Anything else on that one? No. Okay. Any questions? All good? Must be a question somewhere. It'll make more sense when we see get new books as well. Okay, that's I think a good bit to stop for break time again. Come back in about 20 minutes and we shall move. Right, how we all doing? Surviving?
All good.
You'll be saying that next Thursday, after 9 days or so, next Friday. But my God, my head hurts. What's this module 15 about? Hopefully be fine. Hopefully be all good. As I say, I wish I was there instead of here. It'd be more fun. Right, I'll just quickly recap some stuff before moving on to the next section, because quite a lot covered there. Before starting the compressor stall and such. We're way ahead again. There's plenty of time for everything. So plenty of time for recap. Okay, so again, just going back away a bit. Right. So we'll finish on fan balancing there. Who can carry out a trim balance? Who can carry out a trim balance on a compressor? Let's pick a name. Surab?
Yeah, authorized personnel.
Oh, okay. Authorized personnel. Good. Got away there. Good. Authorized personnel. Again, previous experienced engineers who have been selected by the company because you're that good. They've been selected to go or volunteered to go and do a course. But again, if you do courses like that, it makes you more valuable. And again, as I say, it can make you more good salaries. You know, increase your money as well, which is always a good thing. Get paid for being good. When would you carry out a trim balance? When would it be asked to do so? Quite a few options.
When maintenance scheduled.
Yeah.
And report for the vibration, excessive vibration.
Yeah.
While replacement of the blade.
Yeah.
Bleeding repair of the fan blade.
Yeah, sure.
When fitting a new spinner.
Yeah.
When repair of the spinner.
Yeah. So there's quite a lot, isn't there?
Yeah.
Yeah. That's it. Yeah, that's good. What was the term shingling? What does shingling mean? What does shingling mean? Anybody? Pick a name. Prabin? Oh no, somebody's flashing there. Who's that? Parmaswar? Put his microphone on.
The problem caused by the snubber.
Yeah, so what happens there? What happens with the snubber? Anybody?
Snubber may overlap.
Yeah, snubber may overlap. Yeah, we get the term shingling from the mechanism. From good old Americans, they like to name things differently. So when a tile goes another tile, like a roof tile, called shingle. So same for a snubber. When a snubber overlaps another snubber, we call it shingling. So we can unshingle it for a short period only. It doesn't say in the books, but roughly about 20 hours or so. Good. If you're fitting a compressor blade, what sort of lubricant can you use?
As per aircraft maintenance manual.
That's it, yeah. Don't just put your own stuff in there. Don't just go and grab anything off your car or your motorbike or whatever else. Or make sure it's in accordance with the manual. Everything is always in accordance with the manual, isn't it? Okie doke. Right. I didn't mention it on the PowerPoint, but yeah, when you're fitting fan blades to a disc, especially the big ones like the picture we've got there, you would fit them round equally spaced and then probably start at the bottom and fill them round, because if you start at the top and then try and do ones further round, there's a chance that could come spinning round really quickly and also damage your fingers. So again, be very careful when you fit in a lot of blades. Start at the bottom, then work your way around, and the last one should be the top. Now, saying that, because the way the blades are angled, they don't just slot straight in. They do slot in, but some blades are at an angle, so you can only go like a small bit at a time. It's almost like we call it like a mixing wave. You can't just push them all at one go. So depending on the type of engine it is, yes, sometimes you can put them straight in. But sometimes you have to put a little bit at a time, then go all the way around, yeah, until they're all in. But again, that depends what type of engine you're working on. Now, there was two main types of compressor blades. You remember what the names were? Two main types.
Wide and with a snubber.
The wide isn't with the snubber, no. Which one's got the snubber?
No, the wide pod and the that clapper blade.
Yeah, so the opposite of wide is narrow, yeah? So wide chord blade and narrow chord blade. So yeah, which one had the snubber?
The narrow pod.
Yeah, narrow. Good. What was the snubber also called? Two or more names.
Clapper.
Yeah, mid-span shroud. It's rough. It's not quite middle, but we call it a mid-span shroud, a clapper or snubber. Yeah. Okay, good. And what was the purpose of the snubber? What was the purpose of having a snubber on a blade? Anybody remember? So you had the wide chord fan blade, the narrow chord fan blade with the snubber, but the snubber was put on there for what reason?
It prevent the blade flutter or flapping.
Yeah, it strengthens the blade. Yeah, it stops it obviously bending all over the place. It's quite a narrow blade, so it can move quite a lot. So it strengthens the blade. Whereas a wide chord blade doesn't need that because it's short and stubby. So it's quite good. Okay. Example it gives you in the book. I mean, you don't have your book at the moment. A blade that weighs, say that blade weighs about 15 pounds. By the time it's got up to speed, going fast enough, the pressure of the blade root for a 50-pound blade is about 60 tons. I mean, that's like 60 small cars, okay, or two massive Arctic lorries full of pressure trying to pull that blade off. So that's a lot of pressure on a little 15-pound blade. Good. What was the purpose of a containment ring? Yeah, no, not twist the blade. What was it? What was a containment ring there to do? Yeah, it's that's right. Designed to flip the blade should it snap. Because of centrifugal force, the blade should go out anyway, and then flip the blade and then go down the bypass and hopefully land somewhere, not somebody's house, that sort of thing. So designed to flip the blade just in case there's a fracture or something wrong like that as well. Good. On a high bypass engine, what is roughly the percentage of thrust you get from the cold stream air compared to the hot stream air? In other words, how much thrust? Yeah, 75%, thereabouts. It will vary slightly from obviously engine to engine, but roughly all your thrust pretty much is from the cold stream air, from the actual big fan at the front, which provides meaning of thrust, leaving about 25% from the core. So you are still getting a bit of thrust from the core engine, the hot stream, but certainly not quite as much. Okay. What is the name of the twisting of the blades? When you twist the airfoil, what do we call that twisting? It is in an aircraft, yeah, on the wing. It's exactly the same as a wing, but we call it something else in an engine, just to be different.
Shrouded.
No. Starts with an S, right enough. You might do this if you've had too many beers coming back from a pub, as I say to some of my students. Too many gurkha beers, I might be doing this coming back from a pub. Stagger angle. Okay, stagger angle. So it's the same as washout, the twisting of the blade from the root to the tip, but we call it stagger angle. Now, as we go through the book later on, there's also another terminology called stagger angle, which means something else. So there's going to be two stagger angles coming your way. First one is the twisting of the airfoil from the root to the tip. The next one we'll cover later on, but they're both called stagger angle, just to confuse you. Right, materials. What are compressor blades usually made from?
Aluminum and magnesium.
Yeah, the blades are light alloy, yeah, and steel. Now, which way around? Is it the front ones made of light alloy, or is it the rear ones made of light alloy? So the big blades at the front, small blades at the back. Which ones are made of which? Yeah, that's right, because as we go back, the steel has to be a bit stronger, I'll say, so we've got the more pressure going in there, and obviously the increase in temperature as well. Yeah, good. Okay, what are the casings usually made from? For compressor casing? For the housings, casing or housings?
Magnesium and aluminum, or aluminum.
Yeah, good. Certainly steel as well. Good. Okay. I mentioned already, what do we call the type of air that the fan produces compared to the type of air the core engine produces? What's the two names again for the airs?
The stream air and the hot air.
Yeah, cold steam and hot. Yeah, good. So cold steam, again, just what the fan produces at the front, which provides you 75% thrust, and the hot air is your core air. Good. And we'll see the ratios of that when we come to pressures further in the book. All right, what do we call a fan attached to an LP compressor? What do we call that assembly? What do we call that LP compressor instead of being called booster? Good. I guarantee there'll be a question in the book about that. High bypass ratios can be as high as what? Probably out of date now, to be honest, because some of the ratios are being higher than this. But generally, high bypass ratios can be at least what? What's the ratio? Yeah, 5 to 1. Okay. What is the pressure rise through each stage of an axial flow compressor? Yeah, good. And what's the temperature rise per stage for an axial flow compressor?
25 degrees Celsius.
Yeah, good. All easy peasy. How do we maintain the actual velocity of the airflow through an axial flow compressor? You remember the diagram with the velocity going up and down like that, but how do we maintain the speed of the air, the velocity of the air going through an axial flow compressor? Because remember, at each stage it's going to compress.
Yeah, velocity is maintained by the stator vane.
Not maintained by the stator vane. The stator vane directs the airflow at the correct angle to the next rotor, but how do you maintain that airflow through a compressor?
By divergent shape, yeah.
Convergent, yeah. Because of the shape from the large blade to the small blade, we form a convergent shape. So yes, the pressure will rise each stage, velocity goes down, but because of the convergent shape, it goes back up again, up and down, up and down, up and down. And if you get an average, that will maintain pretty much the speed of the air going through the actual flow compressor. So due to the convergent shape. Okay. So yeah, remember a stage is a set of rotors and one set of stators. The rotors being the rotation ones, and the stator, which is also stationary. That makes a stage. And depending on the engine you've got, will depend how many stages you have. Okay. Centrifugal compressor. Give me some advantages of a centrifugal compressor.
Simple and comparatively cheap manufacture.
Yeah, simple, cheap. What else?
Robust in construction.
Yeah. Good, that'll do. What about disadvantages?
Big frontal area,
Yeah.
limited pressure ratio, and high temperature increase.
Yeah. And the main one?
And the high.
Yeah. So high speed of rotation. Yeah. It's a big lump of a thing, so it needs a lot of energy to actually get spinning up to speed. Yeah. Good. Okay. Oh, actually, that one, sorry. What are the rotating guide vanes on a centrifugal compressor made from? Made out of? Older ones are made of this, the newer ones are made of something else. Yep, some modern ones, yeah. So older ones were made of. Not aluminium alloy. The impeller, yeah, sorry, the impeller, yeah, would be aluminium alloy, but the vanes would be made of. Steel, yeah. So the whole impeller is aluminium alloy, but the vanes themselves, they can be reinforced with steel for the older ones. But you're quite right, the newer ones would be made from titanium. Okay, what is the centrifugal compressor is limited to a pressure rise of what ratio? Yeah, 4.5 to 1. Good. Good, good, good. And now it doesn't matter what comes after a centrifugal compressor or a natural flow compressor. What's the next component after either compressor?
Diffuser?
Yeah, diffuser for both, yeah. They both do the same thing. They both operate slightly differently, but they both do pretty much the same thing. The centrifugal diffuser, obviously the air gets spun out by the centrifugal action, out the way. The diffuser catches it in a sort of swirl vane and then directs it to the combustion chamber. The actual flow diffuser is a divergent duct, yeah? So it goes through divergent duct, but they both do the same thing. Both diffusers form a divergent duct. It doesn't matter if it's a centrifugal diffuser or a natural flow diffuser, they both do the same thing. Divergent duct, slow it down, increase pressure, and increase temperature. Now, the increase in pressure and temperature, obviously pressure, it slows down a bit. The pressure helps it for combustion, and also the extra bit of heat helps the air, although it's quite warm already, helps aid combustion, because you've got nice warm air mixing with cold fuel that helps to make a good recipe for combustion. Okay, so when you add spark, it should go off quite easy. If you put cold air in with cold fuel, it takes a bit harder to atomize and combust. So by having the warm air, expands the fuel out as it hits the fuel, mixes together, and get good combustion, which you'll find out also when we do combustion sections. Good, good, good. Right, okay, how do we have time there? It's 3 o'clock. Let's go start the next part, and we'll recap another bit as we finish off. So, what I want to do is I'll go up to, let's see where we are today. Not too far today because we've still got a good bit of the book to do. So I'll go up to, yeah, just a little bit extra. We'll go up to combustion systems, but won't go much further than that for today. That'll be enough. So right, I'll just get into the next part. We're going to look at what's called compressor, stall, and surge. Can anybody tell me what a stall is? What happens in a stall? Going back to your module 8.
Pulse down in high velocity.
Yeah, we basically lose traction of the air. We can't grab onto the air anymore. An aircraft, like you see there, rising off, don't worry about the flames at the moment, but if an aircraft goes too high an angle of attack, plus 15 degrees or so, the air becomes turbulent, which means there's no lift. If there's no lift, aircraft comes down. In respect of an engine, we've got aerofoils in an engine, but they're spinning round, yeah? Now, if the angle of attack of the air hitting the rotor blades isn't correct or too steep, we can get a stall. Now, a stall in a turbine engine is there's no air to catch. If there's no air to catch, there's no air going back the way. If you get a stall in that case, the engine could, the best chance is flame out. There's a surge. Now, a surge is where an stall is complete reversal of airflow. If there's no airflow getting pushed back, but you've got a hot spinning engine at the back, there's only one place that's going to go. It's going to try and go forward because it's increasing pressure at the back of the exhaust. There's no pressure at the front because the compressor isn't working. And all of a sudden you get flames shooting out the front of the compressor as well. And you get sort of a bang or that sort of noise going on, a bit of a rumble. And you see in that picture there, potentially some flames spitting at the back as well. It can damage turbines, it can damage compressor blades. They don't tend to blow up, but it looks quite dramatic. Sometimes you can fix it there and then. Sometimes the damage can be too much, you have to replace the engine. But it depends on severity and depends on the pilot, how quick the pilot reacts. Now, as you can see there, the airplane on that picture here, is aircraft taking off. That's the most likely time a stall or surge is going to happen, is when the plane is taking off. The angle of attack of the aircraft, the speed of the engine, the quality of air going in. Once it's at cruise, there's very little chance of an engine stalling at cruise. Once it's at high altitude, it's sitting there nice and stable. So the most dangerous point for an aircraft is landing, taking off anyway. And add that to mix, if your engine stalls or surges, that adds to the issues as well. So it's the most dangerous point. And also apart from an engine starting up. An engine starting up can also have a stall or a surge because it's not got quite to speed yet. The older engines were prone to stall and surge. The newer engines very, very rarely will stall and surge. Sometimes what might have caused this is maybe a bird flew in there on takeoff or something's damaged it. Or it could just be the settings are wrong, the fuel control management, something that could be wrong as well. A sensor's maybe fail, lots of things can control it. But at the end of the day, what's happened is the airflow has not gone correctly, or the fuel mismanagement or something like that, and it's caused a surge of the air going back the way, total reverse flow. So we're going to look at what's called compressor stall and surge. And a good one to make note of here is, let's get this to work. Look at the compressor stall and surge, what's called the working line. Okay, now this working line, shown in this diagram here, it's the relationship between the RPM, the revs per minute of the compressor, and the mass flow. In other words, how fast that compressor is spinning to the mass flow of air going through the compressor. As long as everything's working right, it will keep working great. When that mass flow stops or slows down, but the compressor's going either too fast or too slow, or there's a mismatch there, then we can get a stall. And we can see in the graph here. So we're looking at the bottom, which is the percentage in RPM of the engine. So 60%, that's about idle. Obviously 100%, that'd be full power. Cruise is about 80, 90%. Now you can see at the lower RPM, there's more chance of being unstable. The higher the RPM, the bigger the area. In other words, there's less chance of getting a surge and stall. So it's lower, the lower RPM. In other words, if the RPM is getting low, depending on forward airspeed, etc., there's certainly more chance of getting a surge or a stall. We've got what's called a working line. Now that's the green line, nice and green. That's the safe working area. Yes, there's built-in margins to maybe go about it slightly if you're unlucky. Maybe just being a sharp turn or changing weather conditions, etc., or fuel supplies, whatever. But once you go past that, you go to the stability line. Well, this is the unstable area. This is when you're guaranteed to have a surge. So if you're sitting about 80% cruise and for some reason you maybe want to start playing Top Gun, you want to throw the aircraft about like a fighter jet, and it's a big 747, then there's a good chance you're going to end up in this area here, an unstable area. But as long as you fly that aircraft as it's designed to be flown, correct speed, correct maneuvers, attitudes, and all that sort of thing, you should be in this area below the green line, the working lines. Everything should be safe. Unfortunately, mechanical things break. You can't foresee that. That's just one of those things. But if everything's working, you fly the aircraft properly, you should be in this area here, no problem at all. But there is also, as I say, a built-in margin to allow just for a little bit above that, but there's not much of a gap, as you can see there. But the main thing is, low speeds, high chance. Higher speeds, less chance. Yeah. But on takeoff, yeah, definitely. You could potentially get a surge on takeoff. that could be mechanical failure. So what you want to make a note of here, the relationship between the RPM of the compressor and the mass flow is called the working line. I've highlighted in red, so make a note of that one. That's usually a good question that pops up, depending how they write it, obviously. Okay, so make a note of that one. Examples got in your books. Again, you don't have to write books here. I don't have it on the PowerPoint at the moment. It gives an example. If an engine takes in a mass flow, the word mass and flow are vital, of say 10 pounds of air per second at the front, then there must be, go back to Bernoulli's theorem, there must be 10 pounds of air coming out the back. Mass goes in, mass comes out, that can't change. However, the 10 pound coming at the back is going to be much greater volume because we've set fire to it, we've added fuel, you know, and the speed's coming out greater. So much greater volume than 10 pounds going in the front. That means the velocity must be greater. It's when that velocity changes, that's when, going back to the working line, that can come into effect. So it's the job of the compressor to organise that mass flow into manageable units that the engine can cope with it. If it doesn't match, again, we go into this unstable area here. So as long as the compressor's working okay, as long as the rest of the engine's working okay, there's no damage to the turbine, the exhaust nozzle, the fuel flow control management's working. In other words, everything's working okay. In theory, there should never be a stall or surge. Flying conditions, altitude, temperature, pressure, the pilot, or even the engineer, you know, can cause a surge. Now you can cause a surge on the ground by moving your throttles too quick. When you warm an engine up, you'll start an engine, again, hopefully everything goes well, and you sit at idle for a couple of minutes. And then you go do your power checks. Again, you'll be checking the temperature of the day. Is it a cold day? Is it a hot day with high humidity? Are we going to have potential icing problems? Then you progressively move the throttle up to maximum and check your settings. And once you're happy, you'll bring it back down and let the engine stabilise again. But if you bring the throttle down too quickly, then back up very quickly, you've not let the engine stabilise, and they could potentially what's called overfueling the aircraft, and that could potentially cause a surge as well. So again, it's down to the engineers, the pilots, to operate that aircraft in the correct manner. But again, you'll go through lots and lots of training on simulators before you even get to starting aircraft. Some of you might have been involved in starting aircraft. I don't know, anybody been involved with starting aircraft? Not yet. You'll enjoy it. It's good fun. It's good fun when it's going well. When it goes wrong, you've got to act quick. I'll give you a little story. One of my juniors, he was doing the training on the simulator. Lots and lots of training we used to do in the simulator. And then he passed out. He got qualified. So me and him went out to do an engine run on a Tornado aircraft, like the one in the photograph that I showed you at the front there. And it was his very, very first real engine run. It was just a straightforward, we were doing a quick check. There was nothing special, so only two of us. I was a safety person on the headset. So he starts the engine up, all good. Well, it's to stabilise, all good. Once he was happy, I told him to power up. That was the signal to power up. And he went up to maximum. Took the readings, all good. Once he's happy, brings the throttle back to idle. Again, all good. Everything's going fine. Everything's going fine. And then we do what's called a slam check. Now, this is where we let the engine stabilise and we go to full throttle as fast as we can. We push the throttle as quick as we can, and then we time how long that takes. He'd done everything right. It wasn't his fault. It was one of these things. What happened? Engine stabilised. Great. He put the throttle forward as quick as he could, and all he heard was that noise. Classic sound of an engine stall and surge. And not what you want on your very, very, very first ever ground run. He turned his head from the cockpit, looking outside to me. I looked at him, and he froze. He just froze. And I was shouting at him, bring the throttle back, bring the throttle back. And he just froze and indicated to do that. He eventually brought it back. It seemed like eternity. It was only a matter of seconds. But he came back and we sorted it. And then also, because I had the surge, we'd have to go and investigate the engine, what was going on. He came out white as a sheet. You don't expect to get a surge on your very first ground run. It was just one of those things, totally unlucky. He'd done everything as been taught. It was the aircraft that was playing up with him. It was the engine's fault. We did a few checks, visual checks, checked the front, checked the back, checked inside, no damage. So we checked the settings on the computer, a little tweak, we ran it, and I got him to run it, because it's just like falling off a horse, you get back up again, and everything was fine. Spent a couple of hours obviously sorting it all out, but it was certainly, for his first engine run, an eye-opener. I've never seen a guy's eyes go so wide in my life. Good fun. So when you become trained up, you become authorised to ground run, just be prepared. It might not go right straight away. Not your fault, it just could be the engine's fault. But 9 times out of 10, it will be working okay all the time. But you've got to be ready to react when it goes wrong. Okay, but enjoy, it's good fun, good fun. All right, it's a good little story there. Okay, excuse me. So, all happy with the working line. All right, so compressor stall surge, as I say, the angle of attack for the airflow moving onto the blades is crucial. Okay, so the angle which the airflow strikes the blades, dependent on how fast it's going, the blades are, and the rate of linear flow. So like a wing on an aircraft, the angle of attack on a wing, depending how fast the aircraft's going, depends how much lift it gets. Well, we're not getting lift on the airfoil. We are, it's almost like a propeller. Remember, I spoke about module 17. We're getting thrust. So lift on a blade is thrust, the same as we did in module 17. Now, if that angle of attack to the relative airflow isn't correct because of the speed of rotation, then, like an aircraft, it can stall. Okay, this is not so good. Now, an axial flow compressor can only be designed to have the correct flows at one particular RPM and a mass flow. So as we go through the book, we're going to look at things like bleed valves and this sort of thing, and that's why it's all dependent on manoeuvres, engine start time, the temperature of the day, lots and lots of things that can affect the potential. A jet engine is happy when it's going fast. It doesn't like going slow. It can self-sustain. It's the in-between transition from idle to maximum where you've got to move the throttles progressively, okay? Or when you're flying the aircraft, be sensitive to the throttles. Don't be a fighter pilot and the throttles up and down all the time, okay? It's an engine designed to operate at a certain point, nice and happy. Now, compressors, most efficient engine RPM is maximum cruise, 80-90% thereabouts. Limitation of the maximum RPM to a little above that. So they like to be in the high RPM range. That's when they feel most comfortable. Some control of airflow below design is usually necessary. Okay, so to control that, it doesn't like going too slow, or things like that can happen. Yeah, that wakens you up. So the same as what we saw before, had a bit of a surge there. Now, what I would say there, he's actually in thrust reverse mode at the moment. I can only tell that because the cowlings have moved backward. See that gap there? That means he's actually landing. He's in thrust reverse, and he's had a surge. That's not a good combination. That's definitely the reversal of airflow, but at the wrong time. Okay, so he certainly would have woken up there. So compressor stall, make a note of this. Compressor stall, I've mentioned it briefly already, can be recognised by vibration. So you can feel that in the floor pan, depending on the size of the aircraft. It's quite obvious. You can hear it as well. So I get a rumbling noise. It's almost like a machine gun noise, a low rumble. And the inability of the engine to accelerate as well. And along with that, you'll get a rapid rise in exhaust gas temperature, the EGT gauge. So it will happen very quick. You'll be watching as you start an engine, your RPM gauge is going up, then all of a sudden they'll start fluctuating, and at the same noise, you'll hear a rumbling noise. You'll put the throttle forward, as you maybe were putting the throttle forward, and there's no reaction. All you're doing is adding literally fuel to the fire. You're going to overheat the engine. So your EGT, your RPM gauge will probably fluctuate. Your EGT, exhaust gas temperature gauge, will rise very rapidly, and I mean almost as fast as my hand is going there. Then you've got to react. You've got to pull that throttle back, and hopefully it will settle down. The quicker you react to it, the less damage there is. The longer you leave it in a vibration like that, a stall, the more damage that can potentially happen. If you're really unlucky, you can get what's called a locked-in surge. So even though you've put the throttle back, it stays in a surge. Now, it comes down to experience. Don't try this unless you've been authorized to do it. You can actually go through it. You can put the throttle forward, and that can sometimes blow it out. But again, you only do that if you've been trained up to do that. Normally, though, a simple moving the throttle backwards to idle, worst case scenario, if you get a really bad one, you just shut the engine down. Lock the fuel off, and that will shut it down. And they can go and diagnose what's happened there, hopefully. Okay, so make a note of these ones. So stall and surge, vibration, rumbling noise, inability of the engine to accelerate. In other words, the engine's getting faster, but there's more fuel going in. Well, there's more fuel going in, the exhaust gas temperature is going to rise, and then that's when you have blades and flames shooting out the front of the engine, and they should go out the back of the engine. So if you don't catch it quick enough, it'll explode. Okay, we don't want exploding engines, but no, it would take quite an extreme amount to actually explode the engine. Okay, but you will be trained on this, so don't panic. So we mentioned that we need some sort of airflow control. Okay, now this is a photograph taken of our engines we've got in the hangar. If we go back to the basic engine, you've got your intake and the compressor. Now, normally, as part of the intake, there's struts that hold maybe the intake ring onto the front of the compressor. Now, those struts are called IGVs, inlet guide vanes. These are fixed, and they're the initial, apart from just holding the structure, they also guide the airflow from the spinner to the outside of the blades at the correct angle. Okay. Now, fixed ones are fine. They just, as the air's coming in, it could be swirling about. They just sort of guide the air down to the compressor. That's fine, but we need a little bit more control. Maybe the airflow is too much for the engine. So after a set of IGVs, inlet guide vanes, we'll have a set of these ones. And these are called variable IGVs or VIGVs. Okay. Now say the variable because they can actually move. You can just see where my laser is. There's like a ball bearing, okay, or a pivot point. So these blades actually move back and forward. They're controlled by fuel pressure. Now they can be mechanically controlled. They can sometimes be controlled by FEDEC, the brains of the system. Now the VIGVs, they do the same job as an IGV, but as they are variable, they move in proportion to the RPM of the engine. Okay. Now at the moment, you can see in this picture here, you can see quite a lot of the blade. Now this is in the actual engine switched off, which is the position it would be in. So at low engine speeds, you will see most of the blade, most of the face, so like that, okay, like my hand. As the engine speeds up, they will move out of the way into the position of the relative airflow. So in this position, they call the position the maximum whirl. Apologies for my accent, some people laugh at it. It's WHIRL, maximum whirl, maximum disruption of airflow. So what they're doing, they're holding the air back a bit to direct. You can just see behind these blades, there's the rotor blades, there's another rotor blade behind them. All they're doing is directing the airflow at the correct angle proportional to the engine speed. Once the engine gets faster, as I said there, the blades will move out of the way into the minimum, easy for me to say, the minimum position or minimum whirl. Okay. In other words, we don't need them in the way anymore. The engine is now coping with the airflow going through the compressor. So these will move out of the way and you would see more of the compressor blades. Okay, so maximum position at slow speeds, minimum position at high speeds. So it's a way of controlling the airflow as it comes into the compressor. That's one control method. All they're doing, maintaining the correct angle of attack onto the rotor blades. Okay. There we go. Inlet IGVs and VIGVs. So there we go. IGV, there we say, set of stator blades with purpose to give whirl. That's what I'm trying to say there. Maximum whirl and minimum whirl. Okay. So ensures presenting the first stage of the rotors, the first rotor blades at the correct angle of attack. And that's a mechanism sort of schematic. I'm just going to, you've got yellow for LP for low pressure, red for HP. Servo pressure is the sensing line. It senses what's going on in the system. You've got a high pressure rev, min's a pressure signal, whatever happened to the pressure within the engine. You have a reference pressure, a sensing fluid, and then a bleed air. Okay, a bleed air point. Now this contraption here, if you look at this one here, that blade there is one of those VIGVs, okay, which is one of these. Okay. On this type of engine, we've got another thing called a bleed valve. Now this one just happens to be like, if you can picture a big circular band going around the engine, which moves forward and backwards. So you've got the VIGVs, which move controlling the airflow onto the rotor. Then we've got a bleed valve, which opens as as it says, to bleed air away from the rear of the HP compressor. It's slow speeds only, okay, because it can't cope with all the air coming in. So this blade, the VIGV, is controlling the direction of air, and the bleed valve is controlling how much air at the back of the compressor. And what it does, it stops the compressor from choking, having too much air. Okay. Once the engine gets fast enough and can handle the air, that bleed valve will close. Now you can see it's all connected to the same mechanism, controlled by an actuator assembly, which is controlled driven by the gearbox, and depending on the pressure of the fuel, will move the actuator accordingly, depending on what speed the engine's doing. This is the base. This is for an old type engine. Mechanical one, newer ones are driven by FADEC, which is your fuel authority digital control, the brains of the engine. But all they're doing is controlling the angle of attack of the air and controlling how much air is in the back compressor to prevent choking. Okay. So let's go from the front again. We've got IGVs at the front, the stationary ones. VIGVs, the ones that move back and forward, okay, in conjunction with the bleed valve. Now, once you get past the first stage of rotors, on some engines, especially newer ones, they've got VSVs. There's a lot of V's in this, okay? Now you've got variable stator vanes. You've had variable inlet guide vanes, you've now got variable stator vanes. So in front of this, there'll be a set of rotors, your VIGVs, and then your IGVs. So imagine there's a rotor in front of this. Then you've got these variable stator vanes. These, you see a little linkage at the top here, there's another linkage there, okay, and there. And these are typical of the newer type engines. Now these are controlled by the brains of the engine. Again, what are these doing? These are pretty much doing the same job as your VIGVs. They're just the stator vanes, which are normally stationary, but for depending on the size of engine, will depend on how many stages of VSVs you might have. In this case, we've got 4. They do the same job as VIGVs. They direct the air depending on the speed of the engine, again at the correct angle of attack, onto your rotor blades. That's all they're doing. Have more precise control of the air. Yeah. So there's a lot of movement going on within the airflow. Again, until the engine gets up to speed. Once it gets up to speed, you can see the angle has been moved here. Once it's up to speed, then yes, they will get out of the way of the airflow, and the engine will be happy. All right. Okay. So a lot of V's involved. So I mentioned FADEC. FADEC is your full authority digital engine control. It's the computer that controls these. And we'll speak about FADEC further in the book, but just be aware of the terminologies at the moment. All right. Another type of bleed valve. Saw in the previous diagram, schematic, it was a bleed valve. That was a big circular one. It moved back and forward. You might have what's called a gate type bleed valve. I call this one the cheese grater. I need to get a photograph to send you. It looks like a cheese grater. Basically, it's got a row of slots that move backwards and forwards. Okay, you can't see in the diagram here, but these slots will move backwards and forwards, which will bleed air or not bleed air. Again, proportional to engine speed. They will be open at slow speeds and closed at high speed. And as mentioned, this bleed air will be tapped off from maybe about halfway through the compressor, and it prevents the choking of the back of the compressor. So at slow speeds, the compressor can't handle this air, so it bleeds a little bit off. But as it gets faster, the bleed valve starts to close and close and close and close until the engine's self-sustaining and happy at whatever RPM, because you don't want that open when you're taking off. There's no point in bleeding air when you're taking off. That wouldn't work. So at slow speeds, until the engine is happy, the required RPM, that will be open proportionally to the speed of the engine. So you've got bleed valves, you've got VSVs, VIGVs, IGVs, all working together to maintain the airflow at the correct angle and making sure the compressor, the back doesn't get choked until it's happy at whatever speed it's working at. Okay. All right, let's see. The next one. But the FADEC engines I mentioned there's a little schematic FADEC. You've got the FADEC will control, or the electronic version will control your VSVs, your variable stator vanes. It will also control your VIGVs, also control your bleed valve. Again, all controlled by FADEC. All right. Fully authorized digital engine control. So there'll be sensors, electronic sensors, giving positions of all these components back to FADEC, the computer, and then, excuse me, then the computer will say, okay, I need to move the valves open more or close them more, depending on what's going on. So it's constantly sensing what's going on. Now, you don't have the books there. I can't remember. Yeah, in your books, it won't be in the books you've got at the moment, but make a note of it. You've got the variable stator vanes, your VSVs, contains what's called an LVDT, stands for linear variable differential transformer or transducer. All that is a sensor that gives the position feedback to the FADEC system to let it know what position the VSVs are in. Okay, and the computer will respond and say, okay, they're in the right position, leave them as they are, or they need to move them. Bleed valves, again, position controlled as with the VSVs, but the variable bleed valve is also programmed to allow for differences in N1 speed. Okay, again, until you get your books, you can't really highlight that, but just make a note of that for the moment, a bit of paper, possibly. So VSVs have a sensor called an LVDT, linear variable differential transducer, sends information back to the FADEC, the computer, and that will react accordingly. Whereas the VIGVs, the VBVs, the bleed valve, that will reference speed to the N1 signal. N being for speed, 1 would be your LP spool. Okay, that's about there. Right. Okay, yeah. Let's see where we are there. Okay, right. I think we'll do. That's a good point to go for a break. We'll go for a break. I won't do any more theory. We'll just do a bit more recap of what we've covered there. And that'll finish off for today. So go for a break for the moment, guys. Again, come back about 20 minutes or so, and we'll just do a 15-20 minute recap of what we've covered for all today. That's more than enough for today. That's what, 59 pages, yeah. More than enough, day one. Okay, any questions so far before food break? All like that, all good. Okay, guys, come back about 20 minutes, and we'll see you then. Okay, I'll do some abbreviations and so you can tell me what they are. So I'll go. Just see this one out the way. Blank one up. Right. Who can tell me what a VSV is?
It's variable angle stator vane.
Variable stator vane, good. What is an IGV?
That is inlet guide vanes.
Yeah. What is an VIGV?
Variable inlet guide vanes.
Okay. Let's see you remember this one. What does LVDT stand for? Good, good, good. And what does it do?
It gives a feedback to computer to tell the system actual position of the valve.
Yeah, of the VSVs. And goes back to the computer. What do we call the brains or the computer system that operates?
It's FADEC.
Yeah, that's the ones in charge of absolutely everything. Okay, the bleed valve. Now, you take a tapping of the bleed valve halfway through the rear of the compressor. What does it prevent? What does the bleed valve prevent?
Prevent the choking of the rear stage.
Yeah, just in case there's too much air builds up, you can't cope with it. It's blown up too much. It'll bleed a little bit out. And is it open or closed at slow RPM? 50-50. Open or closed at slow RPM?
Slow RPM open, I think.
Yeah, that's right. Because remember, the compressor can't quite cope with all that air coming in. And once it gets fast enough, in other words, once the engine started to expel the air at the back end, so the valve will be open at startup, and as that engine can cope with the airflow and mass airflow going through, it will start to close off. And then eventually, when the engine is stable and happy, it will remain closed. Because remember, you don't want to open when you're taking off, because it's just going to go blah, like that, you know, bleed out the air, so not good there. So yeah, okay. What was the one we asked you there? Oh yeah, the VIGVs, the variable inlet guide vanes. There's two positions, although they vary from a certain position to another position. What's the two main positions I mentioned? Do you remember the name that's given? There's one like that, and there's one like that. But they do obviously vary in between that. If I give you a clue, if it's at high RPM, will the VIGV be like that, or will the VIGV be like that? That way, or that way? At high RPM. What do you think? So for that one, maximum or minimum at high RPM? Yeah, confidence. Don't go maybe, just be confident. Yeah, minimum whirl. It's called whirl. Okay, it sounds different in different accents around the world. In Scotland, we call it whirl. They probably might say it a different way. Okay, so maximum, minimum whirl. So maximum deflection, slow speeds like that, like my hand is. And as the engine gets faster, it moves out of the way to minimum whirl, which will, the engine's now self-sustaining and it's happy. Okay. So the picture in your books, I mean, if you've got the same picture, no, I can't remember, it's an old book. It'll show you a variable like guide vane picture, and that actually shows you the engine in the closed position, the shutdown position. A compressor stall is recognised by four things. Compressor stall.
From vibration.
Yeah.
Rumbling noise.
Yeah. Yeah, loss acceleration. And the one you don't want to see, you're looking in the cockpit.
Rise in exhaust EGT.
Yeah, rise in EGT, and it goes pretty fast. It's pretty much as fast as my hand goes there. Okay, it rises very quickly, and that makes your eyes tend to go as wide, as quick as that gauge goes up. You go, oh my goodness, all right. So yeah, and you've got to react very quickly. Right, so don't worry about that. Okay, you will all experience a stall at some time. Even as a qualified engineer, once you're fully trained to do ground runs, engine runs, you will all experience a stall at some point. It might not be for years, it might be straight away like my colleague, but you will probably all experience one at some point. But you'll be trained, you'll know what to do, okay, by that point. It's good fun. Just gives you more work to do. Okay, what do we mean by the, what was I going to say there? Yeah, what do we mean by the working line with reference to compressor stall and surge? What's the relationship between?
Is relationship between RPM of the compressor and the mass flow of the air.
Good, good. So if there's a mismatch with that at any point, then it will go above the safe working line, or the working line will go past the stability line, and then that's a good chance you will have stall. Surge. Okay, good. Yeah, good one to make a note of there. All right. Okay. So yeah, we'll just go back a little bit. But I'll go back to day one. It is day one. Go back right to the start because that's covered that bit. Just a quick recap, and then we'll finish off for today. What is the universal gas law equation? Seems like ages ago. What is the universal gas law equation? Thing on here.
P1 V1 by T1 equal to P2 V2 by T2.
Yep. And if I said to you, so let's see if this works. Let's see. I'm trying to draw this graphics tablet. It's better than the pain. So V1 over T1 equals P2 V2 over T2. Hopefully that's worked. Right. So if I said to you, Charles' law, what would that be a constant? So what would Charles'
Temperature
law be?
constant. Temperature
Charles' law?
constant.
No, next one.
Charles law. Pressure constant.
Pressure constant, yeah. So we can get rid of that, and we can get rid of that. That leaves us, oops, excuse my drawings there. That one and that one. So if anything's constant, you just get rid of it. And that leaves us V1 over T1 equals V2 over T2, which means is that directly or indirectly proportional?
Directly proportional.
Yeah, directly. The easiest way to remember, guys, if it looks like a fraction, it means it's directly proportional. Okay. So if I put back in, let's get my pen working again. I'm not the best in this graphics tablet. I do apologise. Oh my goodness, that's rubbish. Oh God, it's because it's an angle. This is quite hard to draw. Oh, it's not a 2, it's a 1. Right. So if I went back to constant temperature, what law would that be?
Boyle's law.
Boyle's law, yeah. Think of Boyle's law as in boiling a kettle or something like that. So we can get rid of if it's constant, we get rid of it. What have we got left with? Well, it's not a fraction anymore. They're in line, so it must be inversely proportional. In other words, if pressure goes up, volume goes down. Yeah. And don't worry, we won't do any calculations in module 15, but just be aware of those type. Good. What was the formula for power?
Energy over time.
Equals energy
over time.
Time. Good. My very poor squiggles there. Okay. Good. And nobody should get this wrong, hopefully. I'm going to draw very badly. And if I said that's the airflow going that way, what type of duct is that?
Divergent.
Divergent.
Good. So with that in mind, let's change the colour. Okay, I'm going to put that V, P, and T. What's going to happen?
Velocity decreases, pressure increases.
Yeah, good. Okay, so as I said, if you turn that on its side, make a rocket. Oh, that's rubbish. Oh my goodness, I need to practice on this graphics tablet. Right, there's the nozzle of the rocket on its side. Okay, so you've got exhaust gases coming out there. Well, you've got a divergent shape. So it'll be velocity is decreased, pressure and temperature increase. I'm not going to that's rubbish. Okay, good. Good. Right, and piston engine, gas turbine engine, which one has the large mass of air with a low velocity?
Gas turbine engine.
No.
Piston engine.
Propeller is a large mass of air with quite a low velocity, but a gas turbine engine is low mass of air, high velocity. Okay, good. Okay, what was a spool?
Pool is a
Compressor,
combination
shaft,
of-
and turbine. Compressor, shaft, and turbine.
Good. Where would P3 be? Where would you find P3?
P3 will be HP compressor delivery.
Yeah, good. Good. Two basic types of ice protection. What's the two types of ice protection?
Anti-ice and de-ice. Anti-icing and de-icing.
Yeah, that's the two methods. What's the two types?
Electric
Heat and-
and pneumatic air type. Yeah.
Yeah, hot air. Good. Okay, so you've got two types of cycles for electrical. You've got fast cycling speed and slow
And,
cycling speed.
Slow.
Which one would be for high temperature, high humidity, or high
Cold one.
moisture? Which one?
Slow cycle.
Fast cycle.
Fast cycle, good recovery. Yeah, fast cycle, just like high temperature, high moisture content. Okay. If you get an example in the question, it might say high temperature, high moisture. It might say high temperature, low moisture. Just think high. Yeah. Good. Two types of compressor.
Axial and centrifugal.
Yeah. Which one has a pressure rise of 4.5 to 1?
Axial.
Oh, 4.5 to 1.
Centrifugal.
Centrifugal, yeah, centrifugal, good. On an actual flow compressor, what is the temperature rise per stage? What's the temperature rise per stage for an actual flow
20.
compressor?
25 degrees Celsius.
25. And what's the pressure rise per stage?
1:1 to 1:1.2:1.
Yeah, 1.1 to 1.2 to 1. Yeah, good. Good. Okay. Two basic shapes of compressor blade, or types of compressor blade.
One is narrow chord blade, other is wide chord blade.
Yeah. And which one has the clappers on it?
It's a narrow chord blade.
Good. Oh, easy peasy lemon squeezing. What is an advantage of a wide chord fan blade?
It's lighter, shorter, move more air for a given RPM,
Yeah.
more rigid.
Yeah.
It has more 4% of efficiency than the narrow one.
Good. Okay. Fan balancing. Who can carry out a trim fan balance?
It's the experienced engineer.
Yeah. And authorized to do so, yeah. Good. Okay. What is shingling?
Shingling is a overlapping of the snubbers.
Yeah. And can we unshingle it? Can we yeah. And for how long?
For the very short.
Yeah. Short time only. It doesn't say in the books. I think the old books used to say 20 hours. It's roughly 20 hours, but don't worry about the time. Just for a bit of background knowledge there. But good. Right, and let's see where we are there. Well, done that one. Right, who can tell me what FADIC stands for? We'll cover
Full
one bit.
authority digital engine control. Full authority digital engine control.
Yeah, good. Full authority digital engine control. It's the brains of outfit. Older engines didn't have FADIC. When I worked on Tornado at the aircraft in the photograph, we had a thing called the DECU, Digital Engine Control Unit. Same sort of thing. I've never worked on FADEC, but the principle is the same as the DECUs that we used to work on in the military. Just a different name for it. The brains of the engine. Okay, good. Alrighty, folks. Right, I'm more than happy there. What time on there? About 10 past. Right, I think that's a good bit to stop. We'll start off with burners tomorrow, so that's where the fuel flows into. Then we'll look at the hot part. So we've covered the cold part of the compressor, bleed valves, VSVs, VIGVs, and that sort of thing, a bit of history. And tomorrow we'll start on the hotter part, the burners, combustion chambers, and that sort of thing. And then we'll finish on probably thrust reverse and bits and bobs. Okay. Any questions, guys, before we head off today?
No questions.
Oh, I like it. All good. I hope to say, hopefully you will get your new books very shortly. I'm sure Sanjeev will be busy weaving away, printing off the new books. So yeah, make notes on your old books at the moment, or a bit of paper, and then just transfer it to new books. Get your highlighter out, and it'll be fine after then. Okay. But otherwise, folks, yep.
Sorry, compressor install and sorts once again, sir.
Say again, sorry.
Compressor install and sorts once again. Can you explain once again?
So compressor what?
Surge and compressor install.
Oh, sorry, compressor surge. Yeah, compressor stall and surge. Okay, compressor stall is when the airflow, the angle of attack, is now too much for the compressor blade. The airflow is probably slowed down, or the RPM of the engine slowed down for the air. It can't grab onto the air, so it's now got turbulent air. There's nothing to grab onto. Okay, unfortunately, the back of the engine that's hot and spinning, it's now got lots more pressure. So you're going to get a rise in EGT. You'll get a rumbling because you've got the turbulent air within the compressor. Unless you catch it quick enough, you might get a surge coming out the front end of the surge. A surge is a complete reversal of airflow. In other words, instead of the air going back the way out the engine, it's now coming forward. And the rotor blades at the front, there's no air to catch onto. It's turbulent air. And the compressor will slow down. Okay, but unfortunately, the back end of the engine, you've got the hot stuff trying to go forward. All right, so basically, the airflow isn't at the correct angle of attack for the compressor blades. Okay, so remember the signs of a stall: rumbling, high EGT, lack of acceleration, etc. Okay, and that's it. Unfortunately, you might get a flame coming out as well because you've got that excess heat in the back. Well, it has to go somewhere, and you've got that extra fuel coming unless you bring the throttle back to either stop the fuel flow or shut the engine down. The photographs you saw there were the aircraft taking off or even landing. You'd actually reverse thrust there where you put the throttle back and you got a surge. So there'd been a choking. Maybe the bleed valve hadn't opened properly enough, stalled the compressor. The compressor's basically slowed down too quick compared to the rest of the what's going on with the airflow in the engine. Okay, remember the turbine's connected to the compressor, so although the compressor slowed down, that means the turbine must have slowed down. But they've got that hot gas that needs to go somewhere, and it won't go out the back if the compressor, if the turbine slowed down. So it's probably try and come forward. And that's when you see flames. Yeah, you get flames shooting everywhere, which always it wakens you up. Yeah. Okay. Anything else, guys?
No.
Okay. Well, have a good night's rest. Sleep well and stay safe. And we shall